Today, we're diving into electrodynamics. Now, that might sound intimidating, but these are basically the fundamental rules for electricity, magnetism, and even light itself. And this isn't some dusty old theory. No, it's the invisible architecture that powers pretty much our entire world, from the phone that's probably in your hand right now to the stars way up in the sky. So, when you're faced with a theory this huge, this monumental, where do you even start? It's kind of like standing at the bottom of a giant mountain. You know the view from the top is going to be incredible, but you're just not sure which path you're supposed to take to get there. Well, it turns out there are two amazing paths to understanding this stuff. The first one we can call the summit view. Think of it like taking a helicopter straight to the peak. You get to see the grand unified theory immediately in all its glory. The other path is the methodical climb, where you start at the very bottom and you build your understanding piece by piece, step by step. The cool thing is, both paths lead to the exact same breathtaking destination. And what exactly is that destination? It's just four surprisingly simple and beautiful rules known as Maxwell's equations. These four lines are the entire foundation of classical electrodynamics. Seriously, everything we're about to talk about, it all comes back to these. Okay, let's do it. Let's hop in that helicopter and take our first path, the summit view. We're going to look at the finished, beautiful theory first, and then we'll kind of work backwards to figure out what it all really means. The first rule is Gauss's law for electricity, and honestly, it's so simple. It just says that electric charges create electric fields. A positive charge is like a sprinkler, with the field lines spraying out. And a negative charge, that's like a drain, with all the field lines flowing right in. That's really it. Charges are the sources and sinks for electric fields. Now, here's where it gets interesting. The second rule, Gauss's law for magnetism, says there's no such thing as a magnetic charge. You can't have a magnetic monopole. You can never, ever have a north pole without a south pole attached. And what that means is that magnetic field lines, well, they don't have a beginning or an end. They just form continuous, closed loops forever. The third rule, Faraday's law, is where the action starts. This is where we see this deep connection between electricity and magnetism. It says that if you change a magnetic field, just by wiggling a magnet back and forth, you actually create a swirling electric field out of thin air. This is literally the principle that powers every single electric generator on the planet. And this is where you see the beautiful symmetry of the universe. The fourth rule, the Ampere-Maxwell law, is just the other side of that coin. It says that two different things can create a magnetic field. An electric current, sure, we knew that, but, and this was Maxwell's stroke of genius, a changing electric field can do it too. And that one little addition, that was the key that unlocked the entire puzzle. Okay, so we've seen the stunning view from the summit. Now let's go all the way back down to the base of the mountain and try that second path, the methodical ascent. This is the more traditional way to learn this stuff, building the entire theory right from its simplest, most basic foundation. This path starts with the absolute most basic thing you can imagine, a single, solitary point of electric charge. That's it. From there, you figure out how to describe its influence on the space all around it, and that gives us the whole idea of a field. Then you have to invent the right mathematical language, vector calculus, to talk about how these fields spread out or curl around. And finally, after all that work, you assemble all those pieces together to build the full theory, which of course is Maxwell's equations. And that's really the beauty of it all, isn't it? It doesn't actually matter if you start with the big, elegant, final theory and unpack what it all means, or if you start with the tiniest building blocks and construct the theory yourself, piece by piece. Both paths get you to the exact same profound understanding of how our universe works. But this right here is where the story gets really good. Because once James Clerk Maxwell put all four of those equations together, they told him something he never expected. They revealed a hidden secret of the universe, a prediction that would completely change the course of science forever. So, remember Faraday's law? A changing magnetic field creates an electric field. And the Ampere-Maxwell law? A changing electric field creates a magnetic one. Well, when you put them together, you get this incredible, self-sustaining dance. A changing electric field makes a magnetic field, which in turn makes a new electric field, which makes a new magnetic field, and on and on and on. It creates this ripple, this self-propagating wave that can just travel through empty space all by itself. And here's the kicker. The equations didn't just say there's a wave, they predicted its exact speed. by plugging in a couple of numbers that you could measure in a simple top table lab experiment, the equations just spit out a very specific number for how fast this wave should travel. And that number is 299,792,458 meters per second. And you have to imagine physicists in the 1860s looking at that number and their jaws just hitting the floor. Because they knew that number. They'd already measured it. It was the speed of light. I mean, what an aha moment. Light wasn't some other weird thing in the universe. Light is an electromagnetic wave. And just like that, Maxwell had unified all of electricity, all of magnetism, and all of optics into one single glorious theory. So, okay, why does a set of equations from the 1860s still matter so much to us today? Well, because realizing that light is an electromagnetic wave is the key to, well, to pretty much all of our modern technology. You see, every single time you send a text, stream a movie, or hop on Wi-Fi, you are using electromagnetic waves. The fiber optic cables that carry the internet around the world, they use light. Radio waves, microwaves, X-rays, they're all just different flavors of the very same electromagnetic waves that Maxwell described. And maybe the most profound thing of all? It was wrestling with what these equations really meant, especially that constant speed of light, that led a young Albert Einstein directly to his theory of special relativity. So, the whole journey of electrodynamics, whether you take the quick helicopter ride or the long, methodical climb, it ends in this beautiful, powerful unification. It really makes you wonder, doesn't it? These 4 simple rules showed us that 3 things that seemed totally separate were actually just different faces of the same thing. What other hidden connections, what other elegant truths about our universe are still out there, just waiting for someone to find the right way to look at them?